Let's analyze a quadratic function in vertex form. Vertex form looks like this: y equals a times bx minus h squared together plus k. Just for this video, let's imagine that b is equal to 1 and let's remove it for the simplicity. Now to get the vertex, we read this value h and this value k, and that's it. We have our vertex. One thing that we need to be aware of is h is going to change the sign. So whatever h is here is going to be negative of that. So if this was minus 5, this would be positive 5. Okay, and to remember this, we can think of transformation of this function. So if this function is to shift on x, it's going to move this many units opposite from what the sign says. Or other way to think about it is we can say whatever is inside parentheses we equal to 0, and then we solve for x. So if we solve for x, we need to move h to the other side. So if it was negative, it's going to be positive, and if it was positive, it's going to become negative. Either way, when you think about it, you should know that the h coordinate, the x coordinate of the vertex is going to change the sign. So in our case, we have plus 5. So that means it is going to become negative 5. So our vertex is negative 5, comma, and then since there is nothing here, we can say, well, it's plus 0. So y coordinate is actually 0. Now that y coordinate is also going to be y coordinate of our max or min. So we can put 0 here, and then we can decide whether this is a max or min. Different ways. We can graph the function on a graphing calculator and see which way it opens. If it opens this way, then we have a minimum. If it opens this way, then we have a maximum. We can also look at the expression itself and see whether the coefficient here is negative or positive, whether we have a minus here or not, right? Since there is no minus, the function is going to open up. If there was a minus here, then it will be actually opening down. So if it's opening up like this, then we have a minimum there, right? So we have a minimum at 0. Let's sketch this vertex and this minimum on our graph here. So negative 5, 0, 1, 2, 3, 4, 5. So negative 5, 0 is right here, negative 5, comma 0. So that's our vertex. Now, axis of symmetry actually goes through the vertex. And the axis of symmetry is a vertical line. So we can say x equals, and then it's always equal to the x coordinate of the vertex. So x equal to negative 5. So we will have a vertical line that goes through this point and cuts the parabola in two symmetrical pieces. So this is our x equal negative 5, and that's our axis of symmetry. Okay. Now range is also going to start from that value. Now let's talk about domain. Since this parabola here is not, domain for it is not restricted in any way, we can always say that domain is all real numbers. X belongs to all real numbers. Or we can say any value between negative infinity and positive infinity can be used in this equation right here. It will work, right? Okay. Now, since we know that the parabola has a minimum, we know it's opening up. So our parabola is going to be going this way, right? And then if it's going that way, then we should be able to say what's the range. Well, it's going to start from the lowest value that it can reach on y, which is 0. So it's going to start from 0, and then it is just going to keep going up and never stop. So it goes from 0 to infinity. But we need to put bracket here because 0 is the part of 0 is included. We could also say, since this is range, y is greater than or equal to 0. It's equal to 0 because this point, the vertex, is part of it. And then it's greater than because parabola is opening up, so any value, any y value above 0 should work. Now, to find the roots is to find x-intercepts, because roots means same thing as x-intercepts, same thing as zeros or solutions. Okay, so to find the roots, we need to find x-intercepts, and in our case, which is obviously pretty simple one, we already have a point that is on x-axis, which is the vertex. And that happened because there was nothing here. It was plus 0, right? So that means the function didn't even move up or down from its original position, from the position of the parent function, which was just here at the origin and then opening up. So to find the roots, now if we are on the x-axis, then the y value, the y coordinate is 0, right? If that's the case, all we need to do is make our y right here equal to 0 and then figure out what the x is. So 0 equals 2 times x plus 5 squared. And now we can solve this in different ways. Now we can simply think which value of x will make this expression inside parentheses equal to 0. If that's 0, then everything else is 0, because this here is multiplication. And we should be able to see that this is actually negative 5. Negative 5 plus 5 will be 0. 0 squared is 0, times 2 is 0, so that's it. X is equal to 0. So our root is 0. But we have a square here, so we would say, well, that's double root. Another way to think about it is, well, how do we find what will make the whole thing 0? Well, we equal this to 0, right? Because it all depends on what x is. So if we equal x plus 5 to 0 equals 0, move 5 over, we get x equal to negative 5. Again, we need to remember that we have a square here, which means we have a double root. Another way to go about this would be to actually get this in so-called root form or factored form. See, the square here tells us there are 2 of these here multiplying each other. So we would have x plus 5 that multiplies x plus 5, right? That means the same thing as x plus 5 and then squared. Now to find zeros, we need to equal each of these expressions to 0. So this one, when we equal it to 0, x plus 5 equal to 0, we get that x is equal to negative 5. And if we equal this one to 0, is the same thing. X plus 5 equal to 0, therefore x is equal to negative 5. This kind of shows us why do we say double root. See, we have actually 2 sets of parentheses, 2 factors, and they happen to be the same. That actually resulted in having our roots being the same. So there are 2 roots that happen to be the same. So that's why we say double roots. So we could also say the roots are negative 5, negative 5, right? We have 2 of them that happen to be the same. So this is how we analyze a simple quadratic function in vertex form. I hope you like it, I hope you understood it, and if you want to see how we analyze some other quadratic functions that are in different forms, please watch the rest of the videos titled Analyzing Quadratics. We have a video that analyzes quadratics in vertex form, standard form, and in the root form. See you in the next video.